2.
What velocity is needed to establish a circular orbit 150 kilometers over a planet of mass with that radius? Okay, so basically we have a planet and we are in orbit around that planet, and so we know that this distance was 150 kilometers, and we know that the radius of the planet was 12.3 parameters, and excuse me, the mass of the planet was equal to 1.35 exponent 30 kilograms. So that was the information I gave you. We're looking for its orbit velocity. So again, the orbit velocity equation comes from the idea of the centripetal force equals v squared over r. So if we solve that for v, that's going to be the square root of ac times r. But the centripetal acceleration, if you're out here in orbit, what's pulling me in toward the middle the whole time is the acceleration due to gravity. So this just becomes g prime. And we know, of course, g prime is equal to g me over r squared. So if I shove this in for that, I end up with v equals the square root of g me over r. But the r squared here and the r that's already there end up canceling the squared part, so we end up with the r underneath it. The other way that this formula looks is just, like I said, g prime times r. But I think this way is easier to plug in given what we have this time. So we have the m already. It's just going to go there. We know what g is. And the r is just going to be these two combined. The problem is I gave them to you in two different things. And the thing that needs to be in here, we'll figure out in just a second, because v has to equal, that's beautiful, come on. V has to equal the square root of big G. Big G, of course, is 6.67 exponent negative 11. And then the mass. What should the mass be in? Well, the mass is in kilograms. Big G, the unit for big G is Newton meters squared over kilograms squared. That's important to pay attention to just because it tells you what all the other things should be. So, to get this, we say, hey, the mass needs to be in kilograms and the radius here needs to be in meters. And so that lets us know right off the bat this should be in meters. So kilo, of course, means exponent 3, so this is 150 exponent 3. Tera is 10 to the 12, thank you. So this is exponent 12 meters. So realistically, if I'm adding this exponent 3 to this exponent 12, it's pretty insignificant. That would be like 12.3000015 type thing, but we can still add them together. 12.3 exponent 12 plus 150 exponent 3. Yeah, we got 1, 2, 3, 4, 5 zeros there before you hit the 1, 5. So, not that significant. I'm sure 2 to 6 figs we can just plug in 12.3 exponent 12 in this case. And then, of course, we need to divide. Oh, I'm sorry, that was my R. Wishful thinking. Okay. Like I said, wishful thinking. The mass of the planet was, yeah, aren't I glad I'm recording this because I look like an idiot. Exponent divided by the 12.3 exponent 12.
2,705.685. I don't know how far you want to go.
Okay, that was weird.
You're a very smart idiot.
Who you calling smart? I got 2710?
Yeah.
Yay! Now, there are gonna be times where that distance above the planet is much more significant, and then adding them would be a critical thing. But I'll have to check and see on that. Hooray!
Yippee.
Hey, that's the right answer too. Are there any others that you want me to,
Can you do the ruler one?
the ruler one up here?
Or like a ruler lab?
The ruler that one? Okay, let's do the one that, yeah, the ruler lab. You guys have a copy of that?
Yeah.
That was off the front there, right? Okay. So, we have our nice beautiful picture where we have going over a pulley. And then we have M1. We have M2. 3. There we have something over here. So, mass 1, oh, we haven't actually put masses on here, have we? Okay, so this was on spot 15. This was on spot, oh yeah, that looks strong, doesn't it? 28. 28, so 2 should really be over here. And then last 3 was at 75. And then this one is at 5. And this one is at 95. Okay, so yeah, originally we were going to mass all this stuff out, so we'll just make up some stuff. So this one, say, is 0.222 kilograms is the ruler itself. So where is that going to add?
It is set.
That's going to pretend that it's right at 50, or somewhere near there. So this would be 0.222. How big do you want mass 1 to be? Let's make it 1.5 kilograms, just for fun. We'll make 2 be 2.5 kilograms. We'll make 3 be 3.5 kilograms. Yay. Whoa. These were little pulleys. So we want to know what mass has to hang over here and what mass has to hang over here. And so, given this situation, again, we say, I want to know that my total torques are going to cancel out, but I have 2 unknowns. To make only one unknown, I'm going to call this my pivot point. If I call that my pivot point, then all 4 of these weights that are on the bottom here are going to try and torque clockwise, but this last one is going to try and torque me counterclockwise. So this one has to balance out all 4 of those if we're going to be in equilibrium.
Okay.
So we're going to have 1.5 times his distance plus 2.5 times his distance plus 0.222, I can write, times its distance, that's a 2, plus 3.5 times his distance is gonna equal my unknown, let's call this side B and this side A, just for fun. So we're gonna have B times his distance over here. And those two sides should equal each other out. The total clockwise should equal the total counterclockwise. Again, since we picked the pivot point right here, that means A has no torque because there's no distance involved. That's why we can get rid of A in that equation. But since that's our picked pivot point, we have to take everything else from there. So if number 1 was at 15 and this is at 5, then the distance in between these two is 10. From 5 to 28, that's a distance of 23. From 5 to 50, that's a distance of 45. From 5 to 75 is a distance of 70. And then B is pulling at 95, which is 90 away from 5. So now all we have to do is plug in that mess and solve for B.
Wait, you're doing like the torque formula, right?
Mm-hmm.
Just-
That's all we're doing is the torque formula.
So all that divided by 90.
So, we have 15 plus 2.5 times 23 plus 222 times 45. 3.5 times 70 equals. So we get here 327.49 equals 3 times 90. So clearly we need to divide those sides by 90. So B must be a mass of 3.64. So we grab it over here. And then we say, how do we do A? There's a long way and a short way of doing A. The long way would be, now we need to call this my pivot point and do the whole equation backwards. We can do that. But the other way is, in this, we are not just in equilibrium with torque, we're also in equilibrium with translational motion, the up and down motion. So that would just mean the total down has to equal the total up. Well, these four together are the total down, and B plus A is the total up. So if I just add these up and subtract B, that'll give me what A is, which of course is much simpler. So if we do that, A would have to equal 4.08 kilograms. And that way A plus B counterbalances all the other four weights.
Aha, I see. Mr. Boston, and like, how did you know to make the pivot point, right there at, like, where the pulley is?
Again, if I'm in total equilibrium, then that means I'm in torque equilibrium at all points. If I would have picked another point, if I would have picked 0, then I would have had to factor in 2 unknowns.
I mean, that would.
And I don't like 2 unknowns because then I can't find out what my unknown is. But if I put the pivot exactly on one of the unknowns, then its torque, since it's force times distance, the distance is 0, so its torque is 0. So at that point, I can just ignore that torque.
Okay.
So you
So
could've
that's
done it
why
on-
philosophically you want to always pick one of your unknowns as your pivot.
So you should have done it on B.
Yes, we could have done it on B and it would have worked out exactly the same answer.
Could you have done it like, say, 50 and just had like a,
Well, if you would have done it at 50, then I would have had an unknown, I would have 2 unknowns. And so when you have 2 unknowns, it becomes much more difficult to figure out what they are.
I knew this was a lot. I spent like 30 minutes trying to figure out how to do rough masses.
I'm sorry. That's why it says loud at the top. Yeah, we can still actually do this lab. But again, I'm just trying to get us to move because it's been so weird lately with distractions.
So then, like, a problem is in the test, we just find the unknown for whatever masses it is.
Yeah, I mean, everything will be given here except A and B, and so that's okay.
Okay.
What other ones did you want to do?
Is there any provisions?
Do the table.
That one?
Yeah.
Okay, that one was like the circular motion number 6?
I still.
Yeah. So I just do 6.
Yeah, let's see. So if we go back to the circular motion one and we look at number 6 together, we have a board hanging. We say the board is 14.3 meters long. That's a long board. And 9.1 meters of it hangs off a cliff. So we've got the cliff here, this distance, 9.1. And then the mass of the board is 24.35 kilograms. So that's going to act at the board's midpoint. And then we got a rock put 1 meter in from the earthbound end. So this is the earthbound end, so 1 meter in. We're sticking our rock. And it's 32.87 kilograms. And then you want to walk out here like a daredevil and see how far over you can walk before that rock's not going to do it for you anymore and you're going to plunge to death.
Okay.
So, if we look at this, we got a couple numbers to figure out. If our total distance is 14.3 and 9.1 is sticking out on that end, then how much is on this end?
5.2.
That was nice and subtracting. So I just subtracted those two, and so now I don't really need to know this.
Well,
Well, I do eventually, but
does it weigh anything?
yeah, this is the weight
Oh.
of the board itself.
Mhm.
So the weight of the board is going to be at the midpoint. So of that total distance, what is the midpoint?
It's at 7.15.
Yeah. So if we have 7.15 is the midpoint of the board minus
It is
the 5.2 that's over here,
1.95.
that means yes, the weight of the board itself acts like it's pulling 1.95 meters. Not doing that over that way.
Oh, so it's like the problem from the.
Does that make sense?
Yeah.
Subtracted from.
Yeah, we just took the midpoint of the board and then we subtracted over, if the midpoint is this far away, we subtract the 5.2 out, and that means it's 1.95. So the weight of the board acts like it's right here. You're gonna be somewhere past the pivot. Clearly this is gonna be our pivot point. So if this whole distance is 5.2 and the rock is 1 meter in from the end, then that means the rock is how far from the pivot point?
4.2.
That's going to be 4.2. So the rock is going to try and pivot me counterclockwise. The board itself is going to try and pivot me clockwise, and if I'm walking out here, I'm going to go clockwise too. So basically these two have to balance out that. So first we're going to say we have our 32.87 is 4.2 away from the pivot, and that has to equal the board, which was 24.35, which we said was 1.95 away from the board. And then you have you, and we said your mass was 72.5
Times your distance.
times your distance. So all we have to do now is solve for the distance, and again, that distance will be measured from the pivot point. The question asked how far out off the edge of the cliff, so how far off the pivot point. So we're just solving for D. If I would ask how far in on the board have you gone, then you'd have to add 5.2 to whatever you get to do. But that's not what I have to. 32.87 times 2.2. So clearly, since this is a plus, I gotta move it with a minus. And then once I get that answer, I want to divide by
The very first.
the 72.5.
There on the problem.
Catch them. Oh, if you're mad.
And we got 1.25.
Yep.
Got two.
So we wouldn't even get as far as the midpoint of the board before it would start tipping on us. Now, if you were a lighter kid, you could go farther out.
Are we gonna find the angle for like number 5?
No.
Oh, why not?
Can we do number 5?
Why not?
Do we got the time?
Totally can do number 5.
Oh, wait.
What problems in which direction, like which way it's going?
Clockwise or counter?
Yeah, do we have to specify the direct way?
I mean, in your little drawing, I always put a little curve just so I can mentally keep track of which one is going which way, but that's all you have to do.
Yes, because it's master.
Okay, if we look at number 5, we had a model airplane of mass 1.25 kilogram flying in a circle tethered by a 1.57 meter string. String makes a 23-degree angle with the horizontal. So compared to horizontal, hanging down 23 degrees, we have our little ship. So if we have this thing, the reason we have that angle, of course, it's the balance between the centripetal force and the wing. So since we know the mass of the plane, then that's going to be 1.25 times g. That's going to go on this side, and so we can easily solve for FC. So this is opposite, that's adjacent, we're going to use tangent. 23 equals 1.25 times 9.81 over FC. These two will trade places. Of course, your calculator better be in degrees, or we will be chatting.
Cool. This one is so easy. Go on.
We're leaving early?
No, this is the same time.
My clock. So that's all the farther we got. So it's this Monday, is that what we're saying?
That's Monday, yeah.
Tomorrow, this really intense study day.
Yes, that's Monday, please.
What?
Tomorrow,
I was so
intense
stupid.
study session.
How about no test? Like I mean, like I know the way the floor is for like.
What are you doing, Marco?
Oh.
Yeah.